start. Okay, welcome at this, I think, third BrIAS event here at the fourth, sorry, BrIAS event. Time flies. It's already now 5 years ago that we had our Homo Roboticus event, which was a very big event in the opera, where we presented our book about Homo Roboticus with 30 questions how we keep in a robotized world, the human values on freedom, equality, and solidarity stand ground in such a robotized and AI world, which led also to the development a bit of FARI, and I think also for this BrIAS on sustainable robotics. And we have again today some interesting speakers, and I want to introduce the first, who is Flynn. He's already a long time postdoc researcher in the Brubotics group, and working a lot on wearable robotics to assist humans, prostheses, and so on. But I think I can give him the floor immediately. Thank you.
Thank you, Parham. Yeah, so my name is Flynn, and I am a postdoc here at the VUB, and working in primarily exoskeletons and prostheses. So technologies, robotics, to assist people throughout their daily living. And I have to move over here more, sorry. Yes. So yeah, I'd like to talk to you about what we're doing in our lab and kind of what our future looks like in terms of what we're going to do this year and compete at CYBATHLON. So I don't know if anybody from Brubotics has spoken before, but Brubotics is a big group of researchers from a very wide variety of fields, everything from life sciences, e-health, engineering, computer science. And we all work together in order to create robotic devices and other assistive technologies that work with people, so that we can get a large range of viewpoints as input to our projects. So, like I said, the first thing that I would like to talk about are exoskeletons. So we work on things like industrial applications. So these two here, one is the back exoskeleton and one is an upper arm exoskeleton. And these are really for industrial applications, workers in the field that are going to be doing work with the devices. This is not where I primarily have been working, but it's something that we have been doing for a while. And we have a spin-off that's going to come out of this work pretty soon here. So just to let you all know that. But really, where I'm working right now is rehabilitation exoskeletons. So a lot of people every year have problems, neurological problems or problems with muscle weakness. And the rehabilitation techniques that are used for these people are very labor intensive and costly. And a lot of times they require a lot of people to get very little result or little time with these people because it's so expensive and costly. So you can see in some of these videos you have 2 or 3 PT workers with one individual for their half hour of time that they have on the treadmill, and that's basically the rehabilitation that they're able to get. So one of the first things that we worked on at the lab were these kinds of fixed rehabilitation devices, like exoskeletons that would be able to help a person ambulate who might not be able to, and kind of replace the requirements of having so many different individuals looking at these people while they're doing their rehabilitation, and also to be able to up the number of repetitions that the people are able to get. So this one is called Altecro, and but you can see it's very hard to move from this to something that's actually useful in daily life. This is something that would be for a clinic. You would treat people in it. And so we also looked at a lot of exoskeletons for assistive technologies, such as in the Parham H.A project, which was a European project, and the BrIAS project was an FAO project. Both of these were designed to reduce the size of the exoskeletons and make them more usable for a wider range of people, and to give assistance rather than so much rehabilitate as much. So these are two projects that we have here. I have part of the myriad here, if you want to look at it afterward or talk about it. Yeah. So we also work on different actuator technologies. We have a general purpose SmartGhost actuator, which was used for a number of different applications in rehabilitation. So we have here an arm rehabilitation thing. One of the things about all of our systems is that we really believe in having serious compliance or compliance, natural compliance in your system to better interact with the person. So we deal a lot with designing actuators that are made to interact with humans while they're going through their rehabilitation scenarios. So, and currently we have a new project called RevelExo, which we're trying to solve some of the problems of our previous devices, but also this one is intended to not only do rehabilitation for a person, but to also provide assistance at the same time. So we'll have one that, for example, for sarcopenia patients whose muscle decline will definitely get worse over time, and that's just a matter of time. So they might need assistance at the beginning that's very light, but also because they can rehabilitate at the same time, they can keep their muscle function for a longer period of time as well with our device. At least that's the idea. So we hope to help individuals retain muscle function for longer by using it in a rehabilitation scenario as a resistance trainer. And then eventually a more assistive role will become of our device. And so we have a number of different systems that we're looking at to incorporate in this RevelExo exoskeleton. One of them being the remote cable transmission, which is seen up here in the upper right there. We implemented a version of this on our stationary exoskeleton, but it allows us to play with where the position of mass is on the person. So we don't have our mass very distal on the legs, which can be very tiring and give people problems. So it can move a lot of the electronics, a lot of the weight to their waist while operating at distal joints like the knee and the ankle. Another thing that we're incorporating into our project here, the video you're seeing here is from SAFER. It's a project that looked at the interfaces between the person and the robot. So in this case, they're looking at it for measuring how the robot is pushing on the person. And we're trying to incorporate these kinds of sensors within cuffs in order to provide assistance, better provide assistance with our exoskeleton, so sensorized interfaces. Yep. We also have prostheses. So prostheses is another large section of our work here at the VABA. And in fact, it's one of the first things that was done here. A long time ago, they were working on pneumatic actuators, and they built a pneumatic actuated ankle prosthesis at that time. And this kind of grew into what was known as the Amfoot line, which led to our spinoff called Achilles. And the project that I started here on, which was called CyberLegs, which is a full knee and ankle prosthesis. So it's a full robotic prosthesis where we would play around with things like energy transfer from the knee to the ankle, different actuation techniques, such as using what we call the McKepa actuator at our, which is a variable stiffness actuator. And so we, throughout the CyberLegs project, came up with a series of different prostheses in order to explore different ways of interacting with the person through replacing their leg. So this is the current design is the CyberLegs X-Leg, which is our most recent design. But the idea was to simplify a lot of our older CyberLegs devices by replacing, for example, the 2 springs in our ankle with a single spring in the ankle, but being able to change the stiffness of that depending on the configuration of the ankle by the mechanics alone. So we have a fully active ankle with our device, and we were able to reduce our weight by quite a lot. So we have people walking with this device as well, and so we're able to reduce the weight of our device and provide very similar behaviors as previously. So our knee is a new design as well. This is a much simplified design compared to our previous designs, and it utilizes a 5-bar linkage in order to get varying gear ratio across our motion. And the major thing about this would be to provide very large torques while you're in flex positions, and very high velocities, relatively high velocities, when your knee is extended with the same motor. So you don't have to have a variable, like a different, it has a variable gear ratio built into the mechanics of the design. So this would help for things like sit to stand and stair climbing, where you need very high torques in your knees, and also during walking or other swinging, leg swinging motions when you need high velocities to swing your leg. So CyberLegs, we had a lot of working devices, and we had relatively decent behaviors back then. And we actually brought this version of the device to CYBATHLON in 2016, which is something in the future we want to bring the new version of our X-Leg to CYBATHLON as well. So another thing we work on is the control of these devices. So control between the prostheses and the exoskeletons is very similar in a lot of ways. One of the easiest ways that we've been controlling our devices is through threshold-based state machines, finite state machines. And as you can see, this is a finite state machine for gait initiation and walking. And the parameters that are there, you can see that there's a very lot of them. There's a lot of parameters. And these parameters for our state machine, we generally had in the past chosen by hand. So we would pick out certain points in the gait cycle and then tune positions and velocities for triggering our state machines. And so this is a very labor-intensive thing to do, and we want to kind of replace that with other methods. So one of the other methods that we've been looking at is phase-based signals. So you find a periodic motion or a periodic behavior within the tasks that you want to do, and you can then apply a phase detector to determine where they are in that phase. And so then you can apply a certain torque trajectory or a certain velocity or a certain impedance values to the controller of your device by, in this case, a lookup table where we apply specific torque to the device by looking up a torque position of our device. That's, if you guys want to talk about this more later, I can make it much clearer. But this is one way to get a continuous signal. The point is, yeah, you get a continuous signal that you can use over the entire range of motion for that specific task. Yeah, another way to do this is this is from Helen Huang's group, but what they did is utilize reinforcement learning on impedance controllers, and they chose specific points within the gait cycle, which are those 4 points down there, to change impedance parameters to their controller. Once again, though, these points that they choose are kind of by hand, and you kind of have to have experience and know what your task is in order to choose these points at which to optimize around. And it's something that, yeah, it takes experience, and it's actually kind of intensive to do because you need to know these things a priori, right? So one thing that we've been looking at is trying to do human-in-the-loop tuning, which means you take a person and you measure some kind of biological output to that person in order to optimize your torque trajectory or your position trajectory of your device. And so on the right here we have a setup from Steve Collins. I don't know if you know him, but they kind of, yeah, I would say originated this human-in-the-loop method in order to determine torque trajectories for ankle exoskeletons and ankle prostheses in order to lower metabolic rate of the person. So when the person would measure how much metabolic oxygen they're using, and using that as a guide for their effort. And yeah, so they can, yeah. What's kind of funny, and this is kind of an aside, but these devices were done with prosthetic simulators and exoskeleton simulators that were off board. And actually, in 1972, they were kind of doing the same thing, actually. They built a prosthetic simulator which was able to measure EMG and kinematics and a lot of different things and apply new trajectories to the person in order to optimize their gait. So it's kind of like what's old is new again, and stuff like that. But yeah, we have better ways of doing this optimization now. So hopefully we can actually converge to a better way, in a better way. So we were using this in order, a human loop method, in order to increase symmetry between the legs of the person while they were performing a sit-to-stand operation. So we have a state machine which is providing it's actually a phase-based torque signal to the knee joint. In this case, we're only optimizing a knee. And we look at the ground reaction forces and see which leg they're actually supporting their weight upon. And so when they support it too much on the prosthesis or too little, we can optimize the torque trajectory of the knee throughout the cycle as well. So, and it was looking to work, and we need to expand upon this a bit more and get it working a little bit better. But hopefully we'll have results from that as well pretty soon. Yeah, and like I said, we're looking to go to CYBATHLON in 2024 this year, which is at the end of the year. It's in October. If you're not familiar with CYBATHLON, it's actually it's modeled after the Olympics, but it's a number of different, yeah, what's it called? Different events which highlight a certain technology, a certain assistive technology, in order to complete a task or race through an event using this technology. So this year there are 8 different fields. Things like the lower limb prosthetics, there's upper limb prosthetics as well. There's wheelchair races and functional electrical stimulation bike races, where they have a person who's fully paralyzed from the waist down, and they stimulate their muscles in order for them to ride a bike around a track. It's interesting stuff. But we're going to do the lower limb prosthetic race. And for this, we have a project called AidWare, which is funded by BOSA. And we're looking at incorporating AI into our top-level control in our prosthetic devices as well at this point. So we're looking at more unstructured environments, trying to create controllers that will apply to a wide variety of different motions through the use of AI. And so this is in collaboration with Liège, who is doing musculoskeletal modeling of the person wearing a prosthesis, and also Karl Leuven, who's doing the AI-based controllers. And what's nice about CYBATHLON is that it requires us to go, oh, I'm sorry, I've been a slide ahead for a while, huh? Sorry. Yeah, so what's nice about CYBATHLON is that it has tasks that are known, but are relatively reasonable for a person to do during their daily living. So things like stepping on stones, like step stones, or doing sitting at a picnic table and not disturbing the people next to you. But these things are not in the literature. These are tasks that are not well studied yet. So we can use our limited data set and gather a limited amount of data for all of these different tasks in order to try to build a controller that will work for all these tasks. So we're going to start looking at a little bit more unstructured behavior and trying to incorporate that in our controllers for our prostheses. So, yeah, and I think that's about it for this. We actually are actively looking for the pilot of our device, so we need somebody who's actually going to come into the lab and wear the device during the competition. So if you guys know anybody who might be interested in this, it might be something that you could help us out. So, yeah. Excuse me. Yeah. So yes, please. Any questions?
Okay, there are questions.
First of all, thank you for your nice speech, and very, very clear. Thank you. And just a curiosity, do you think there is such asymmetry in the behavior of one leg with respect to the other legs? I mean, it's possible to monitor an online monitoring of what one leg do and apply the artificial intelligence to follow with the artificial legs, for example, the other leg behavior.
Yeah, so one of the original, like the first thing that a lot of people try is to do mirroring. So you measure the behavior of one leg and you just play it on the other leg. And that tends to not be a very good way to control a device. One thing that's weird about that, in saying that, is that when you look at symmetry in a person when they're walking, it's actually one of the best signals for that gait being a good signal. So there's kind of a discrepancy between when you control somebody's and force them into symmetry versus when they have symmetry naturally. And yeah, we're talking about this as well, about the different dynamic. There's nothing to say that symmetry would work well, right? Because if you have one leg that's way heavier than the other, then you would expect there to be an asymmetry there. But yeah, still having symmetry in your gait cycle is still one of the best ways of seeing that their gait is a decent gait. So there's a bit of a discrepancy there, yeah. It's very interesting though.
Okay, other question?
Hello, thank you very much. And you touched upon it a little bit, but how do you factor in or measure the acceptance, the psychological almost acceptance of the users? That you showed the different ways you can measure the physiological reactions, and
so one thing you can do is just ask them, actually.
Yeah.
So one of the things that yeah, well, no, it's on this slide. No. Yeah, one of the things we have on our, man, what is going on? Oh, you guys don't even see it. Yeah, okay, never mind. Okay, so it's here, is that we have real-time user feedback. So they can literally just play with the dial to say, I like this, I don't like this, or just give us verbal feedback in order to do that. We oftentimes look for proxies though, like if their EMG is high, we think that they're requiring more effort, and that would be one thing. But like psychologically, this is one way, you just ask them.
Yeah, so following up on this, the human in the loop, the feedback, you are mentioning you visualize some actor-critic reinforcement learning method. I suppose you do a lot of online learning, so you learn from one person and they feedback on the system.
Yeah.
But initially, I suppose there is a lot of error, which in this case may be a lot of pain and discomfort. So how do you adjust the learning to take this into account?
Yeah, you really have to constrict the regions that you're searching. And in fact, a lot of solutions to that won't allow them to walk. Like some things like, yeah, so it's actually quite difficult. You really do have to do a lot of this tweaking in order to them just get a gait that works in the first place. And that is a big problem, yeah, for sure. So you do start with a lot of error. You start with just a general guess, basically, and then, yeah, constricting the regions that you optimize around, yeah.
Thank you for that. On your videos where you see the people getting up, standing up and sitting down,
Yeah.
it looks like you get very different movements out of the artificial knee joints as you do out of the normal knee joints.
Yes.
So are there methods you can try to maybe increase the degrees of freedom that you have in that joint?
Yes. You could allow, yeah, different motions. Right now we're only looking at sagittal actuation, which is limiting for sure. Yeah, we might have to try to incorporate and just be able to study that. It's not something we study directly. Yeah, it would be a new field. Yeah. But it is definitely a good suggestion. Yeah.
You said you were looking for someone who wants to be, I think, the pilot, you call it?
Yeah.
I was wondering, doesn't the previous participant want to join again?
Actually, we haven't asked him yet.
Okay.
So, yeah. So it was a while ago, right? And yeah, he might actually. We need to talk with him. We only just finished our flyer today. So
I see.
We're really at the beginning.
And what are the requirements for this
Basically,
person?
you have to be a transfemoral amputee. That's
Okay.
it. For our hardware, you kind of need to be less than 100 kilos, let's say. Yeah. But other than that, there's no real requirements.
Maybe a very technical question. As it is an active prosthesis, how
Yes.
much like energy, like battery? What's the
Yeah, so right now
for you?
we're using relatively large batteries, and but they can last for 4 hours, 5 hours, no problem. It is not something we've optimized in our current designs. We're more just looking at the actuation, looking at the control to see if it'll work correctly. So there's lots of optimization like we've done there. So like our motor drivers, they burn a lot, they're like 10 watts just sitting there doing nothing. And things like that could be optimized by a lot to reduce battery size. Like,
So, do you plan to have the battery on the person that is having
yes,
the
so our
prosthesis, or-
knee actually, that knee has the battery in it. And it's
okay,
able to
okay.
run both the knee and the ankle device, yeah. That was one big thing about the X-Leg, is that we wanted the knee to have the computing and the battery for both the knee and the ankle. So the ankle only has the drivers for the motor, and all the signals actually come from the knee. We can also separate the knee from the ankle and run them as separate units as well with the same electronics. Yeah, so, but then we wear that on a belt on the if you're just using the ankle. Yeah.
Other questions?
Sorry, I have another one. You mentioned, didn't you, that you'd started a company,
Yeah, Axeles Bionics is a spin-off from this lab.
and how difficult is it for that? I've started companies, and this seems really early stages. So how difficult is it for that company to remain active and generate revenue?
Do you want to answer this?
Yeah, it's a huge challenge because it's hardware, so you need a lot of disciplines to combine. Moreover, it's a medical product, so it also has to be certified. But the company was founded in 2019, and so it's still active, and it survived Corona. And yeah, they're selling now their first commercial product. So yeah, already in several countries, the Lunaris, as it's called, is active, and so they also obtained the SME European Innovation Council Accelerator grant. So that shows that they're still on the forefront of innovation. But it's a challenge for several of our startups that it's hardware related. On the other hand, there is also quite some IP in it, so that's an advantage because yeah, we can protect a lot of things. And so now it's also not only the food, but we're looking to other transfer of IP on knees and so on, to gradually improve the products and services.
Thank you.
Other questions? Okay, I leave the word to
Thank you a lot, Louis. Then I can at once invite the next speaker, from Louis, a very senior of our research, to a starting young researcher, Parham. And so we work a lot in our group, as you saw, on energy efficient actuation, which made it possible to go to the prosthesis and also to the exoskeletons. But of course, it's still battery powered, and batteries needs to be managed. And do we always need all sensors in it? And so that's the idea of Parham, to they investigate energy management and battery management, because we have a lot of robots here in the lab that are battery powered, and due to Corona, the batteries died a lot, so it's not very sustainable. And Parham wants to solve this in the future, to take better care of energy for robots. And I see set up, and I think, are you sharing the presentation online? Is it online? Okay, perfect. Then the floor is yours, Parham.
Thanks a lot, bro. So, hello everyone. I'm Parham, and as Bram just told us, I just started my PhD last year. So, please see me as a really junior researcher here, and also the presentation that I'm providing for you maybe be more on the ideas that I'm going to work, and also I'm looking for your comments and on your feedbacks on my ideas. So today I'm going to talk about the battery and energy management in robotic systems. Usually, mobile robots showcase remarkable abilities from picking apples or lifting heavy loads. And just some minutes ago, Louis shows us the use case of the wearable robots. And you also mentioned about the batteries in these devices. But the performance of these devices are usually limited by their battery life. And unlike the stationary robot system with the constant power from the grid, mobile robots rely on the batteries, which needs frequent charging. For instance, the Boston Dynamic Spot, the quadruped, carries a significant battery weight, which is 8 kilograms, and it's 1/4 of its total weights. And it just runs for 90 minutes. Or the Atlas, the humanoid that they have, we all saw the amazing dynamic movements that it can do, but they never mentioned for how long it runs. And for the other, for the Amazon delivery Parham Air product that they have, the destination that these drones can go is just 6 kilometers, and the package size is just like a shoebox and cannot be more than 5 pounds. So this presents a strict challenge. How do we extend the runtime of mobile robots without making them too heavy to perform their tasks? One solution, of course, is developing of batteries with a higher energy density, but achieving longer operational periods without increasing the battery weight is also a challenge. Recently, some researchers in our group from Brubotics, including Bram and Tom, in collaboration with the other groups in VUB, MOBI, they evaluate the suitability of the different battery technologies for different robotic applications. And in the left, you can see that they evaluate the importance of the requirements, such as a specific energy, the current variation, a specific power, temperature, safety, and cost, and the lifespan of the robot in different applications. They score them, and they score that for the different technologies, battery technologies that they have. I've added the average value here in the table to just show you that the specific energy, which is the total amount of energy of the battery divided by its mass, has the importance and concern of the robotics engineers. And for the in the battery technologies, it has the lowest score. So it's a big issue and problem. And how serious this energy density problem is based on the size of the robot, the structure of that, the function, and how the robot is working, and the examples were in the previous slide. Also, the other thing that's interesting for me is that by the engineering and robotic engineering background, the score of the lifespan of the battery and the importance of that just is for those applications that as the engineers we cannot sweep the batteries. So we thought that if we can sweep the battery or we can just charge the battery, it's a good solution. But is it good or not? I'm not sure. And I think we should see another possibilities and other solutions. So based on that, there are several additional technologies that can be added to overcome the inherent limitation of the batteries. Although often at the cost of the extra weight, complexity of the system, and the money cost. These technologies can be the battery management systems that usually they have the functionality of the monitoring of the battery, the voltage, the current temperature, or estimating the state of the health or state of the charge of the batteries. And the newer versions of BMS, they are capable of communicating with the other control system in the robotic system. And also there are thermal management system and packaging that which mostly it's about the safety aspects of the robot. And also the other interesting thing is about the hybrid architecture that can be used, because high charge and discharge rates for a lot of the battery technologies are not has not a good value. And just having the battery plus battery structures or battery plus capacitors can be a solution. But still there should be new solutions, and this is what we are looking for. These new solutions can push the battery technology beyond its current boundaries and open up new opportunities with this field. The research community these days are working to discover the new way to detect the battery degradation and to slow down the aging phenomena in the batteries. And again, I should repeat my question: how do we extend the runtime of such robotic systems without making them too heavy and now too complex to perform the task? The solution that we are proposing and we are working on, it's energy management framework in the robotics. We are working and focusing on three components on that. First is the context-aware system adaptation, and energy-aware task scheduling, and energy harvesting-aware path planning for the mobile robots. So, for making energy-aware decisions in the robotics and overall in the systems, we need energy management framework. And the goal of this energy management framework is balancing with the performance and the energy goals of the system. And how it works and what's the solution to making this context-aware system adaptation in our systems is based on self-adaptation methodologies. If your robotic system has the capability for self-awareness, self-optimization, and self-reconfiguration, this self-adaptation is a good solution for that. But still, there is a lot of challenges on implementing on that, because when the adaptation space size grows in a complex system, finding the best configuration for your system will be hard. And then we have to use different decision-making techniques, rule-based, model-based, or a hybrid approach for that to overcome this. And in my PhD and in my research, I try to implement this self-adaptation in a small robot, in a turtle bot, to showcase that it's possible, and it's based on MAPE-K paradigm. The MAPE-K paradigm says us that we should monitor our environment. We should analyze the mission, and we should predict the energy for doing that mission. We should plan we should have the planning in our system, and we should a way to execute that. And the input for this paradigm is the functional and non-functional objectives. Functional objectives are what the robot system should do in form of a functional task. For example, if your robot is tracking a line, it's that. And the non-functional objectives are how the system can perform this task. For example, how can it deviate from this tracking line? And based on these decisions, you can complete this loop. And also we equipped our mobile robot with measuring components, and as you see, for a simple task that the computation and the sensors are fixed and constant, they use a constant power. Just two configuration, like a no load and with a full load and with a payload. You can see the measurements, and it's this is the knowledge base that we should make in our paradigm. And just imagine that your robot has a lot of configuration. You need to have all of this knowledge and all of this to do. Yeah. The other thing is that we are going to have energy harvesting over path planning. And by that, we are equipping our robot with a wireless power transmission system. And just imagine that your robot in a warehouse is going from the point A to point B, and it can take the blue path, or it can take the red path. The blue path energy harvesting on our solution, that it goes to maybe the fastest way or the best possible way, but without considering the energy harvesting. And the red path is the one that you consider the energy harvesting your system. And again, how it fits in our context, our solution that we had, it's based on that. Okay, how fast you have to get to your destination, or how much you are allowed to go to other direction that the one that you are now. So these are functional and non-functional goals that I spoke about it in the last slides. So based on that, we can decide which path we get. And also, by means of this, we can extend the autonomy of our system, which increase the system intelligence. And also, with the proper frequent charging, we can increase the battery lifespan, which can also increase the sustainability of our robots. And how this is possible, because as you know that the depth of the discharge of the batteries significantly affect the battery life. So by using this harvesting our path plans, we can just go from using the 100% depth of the charge to a less one, and we can extend the life cycles of our battery and increase its sustainability. The other thing that we are working on is the energy-aware task scheduling. In this part, our colleagues from the Antwerp University are working on the centralized and decentralized task, energy-aware task scheduling, and they are proposing the method that includes the energy consumption estimation, charging contingency approaches, and energy harvesting prediction to minimize the overall task execution time. And the scheduling problem is optimized using the adaptive particle swarm optimization, APSO, PSO, and generic algorithms. And here in this chart, you can see that the computation time of the system when it's energy aware is less than when you are not energy aware. So in some point, it's basically in this way, we can increase the sustainability of our systems. And as I just speak a lot about the power consumption estimation in robotic devices, I also propose a hybrid approach for estimating the power consumption of the mobile robots, ground mobile robots, and which have 3 steps. The first step is the offline mass decouple coefficient estimation of the robot. That practically we should run our robots with a full load and with a no load, and then based on the equations and the models that I provide, we can find these mass decouple coefficients. And in the online phase, when your robot is moving, for example, in a warehouse, and it just with a changing payload, you can estimate the payload, and based on that, you can estimate the energy consumption of your robots. And again, how it fits to energy-aware energy management system of that I talk about. It's because of the second step of this approach do not need to perform continuously. By choosing when to perform and when to measure the inputs that you need and the measurements that you need, you can make a balance between the accuracy of your estimation and the energy that you are using for doing that estimation. And for example, as you see here, if we just use 25 seconds of data in each section for estimating the mass, it will be near, I think, 80% of error in total in our mass estimation. But if you do it with the 100 second time slides, it decreased to the 7% error. And yes, this is what I'm working on. Thank you for your attention.
Any questions?
Thanks for your talk. I have a couple of questions regarding the battery. First is, you started talking about the energy management, but what is an acceptable ratio between the weight of the battery and the weight of the robot fully load? And the second one is, you are talking about energy harvesting.
Yeah.
That means that you are charging the battery while operating the robot.
Mm-hmm.
That means that you will simultaneously charge and discharge the battery. And you are stating also that 100% is an optimal value to keep the battery life. Could you elaborate on that?
Let us start with your second question. No, it doesn't mean that all the time you have to harvest the energy. You should, as you see, for example, this chart for the lithium iron batteries, there is the depth of the charge that you should keep your battery on that. And for generally, for example, for the lithium-ion batteries, they said that it's better than you keep your batteries from 20% charge to 75% of charge. So it doesn't mean that every time that your robot moves and goes on the charging strip, it has to harvest the energy. It's based on the algorithms that you are providing for your system. And for the energy ratio in the robotic systems, I think it's based on the different application, and maybe if you are more exact about which kind of the robots you mean, we can discuss it. And yeah.
Okay. Other questions?
congratulations, very nice talk and very nice topics, very important. Two questions. The first one, on the first slides you showed the very beginning, this one exactly. You are showing several measurements, but which kind of measurements are these? These are direct measurements or qualitative measurements? And how to deal with the uncertainty of these measurements?
Maybe Bram as was the one of
Thank
the
you.
writers there.
Yeah, it's indeed. It's not. It's more an expert evaluation to say. The reason is that, yeah, robots come in very different applications, but that also means in very different uses of batteries. For example, a drone is more or less a continuous current take from the battery, while prostheses, exoskeletons, humanoids have very high peak torques needed, so also peak currents, and sometimes even a part regeneration, so it's continuously like that, which is very different than, for example, computers or EVs, but that also has a huge impact on which battery technology. And so we classified what are the needs of the applications. Some, like humanoids, can fall and they walk, so they have shocks, so that also has an impact on the battery technology. Temperatures, for example, can be very different, and so that we classified, and then we said, yeah, for the different batteries technologies, how they perform for that, and then we gave numbers, good, well, and that made as a kind of decision tree which battery technology is yes or no suitable for which kind of application. And apart from the battery technology, there is also which additional technologies you can add. Because, for example, with packaging you can do a lot. With battery management, thermal management systems, you can compensate some of the drawbacks, or charging, for example. And so that's what is the whole paper about. Because I think currently we use for prosthesis, for example, a battery, but it's in fact not optimized for that application. So I think there is a whole area where further innovation is needed. Battery is optimized for the use cases of a specific robot. But at the moment, robot technology is mostly like a client and takes what is available.
Yes, plus or minus, we have the same problems that had Leonardo.
Yeah.
That has the technology is ready, but they have no power sources to make the helicopter fly, maybe.
Exactly. Yeah.
And second question is, in the last slide, I've talked about the accuracy of the system. And this is very interesting because, of course, accuracy for us, I'm a metrologist, and is a very important topic, but to achieve high accuracy, you need to spend. You need to spend money. In this case, you need to spend energy, so you reduce the lifetime of the robots. But at the end, you you mixed accuracy with error. What do you mean exactly? Because are two completely different concepts. I mean, you are talking about accuracy if you have no references. If you talk about error, if you have the references. So in this specific case, what do you want to do? Thank you.
For me, in my I mentioned the error because we had the reference and we had the real measurements, and then we calculate the error of our estimation, and it was the error was based off that. Yeah. Yes.
Yeah, thank you for the presentation. You had at the beginning 3 different topics that you want to use for the better use of energy. It was like the harvesting and the battery management system. Was there any study or estimation done in which field could be achieved the most, like saving? Because I imagine if you have a robot with sensors and actuators, and you switch off a few of the sensors from time to time, the gain is very limited. So was there any idea of like which one would be the most efficient, or which one would yield the most gains in terms of saving energy of those 3 topics?
I didn't find article or paper that compared these techniques together. But as I just researched, I think the energy harvesting over path planning is one of the most for the mobile robots, at least in the warehouses or the ground mobile robots. But it depends on the technology that you are using and the different application. If it's the wearable robotics, it will be totally different, because there you do not have the harvesting, and then you should optimize the configuration of your wearable device to optimize the power consumption of that.
Other questions?
Sorry for coming again, since Professor Blanc raised the topic. We are clients of the batteries, no, in this case. I was wondering, how are we choosing the batteries in this case? Can we state that the battery is not lasting long enough if we are not choosing it properly? How can we decide that the battery doesn't have a proper lifespan if we don't know how to size the battery according to the application? Have you inquired about this to the users of batteries?
Just let me back to the maybe first slide here. You mean here? Here it's a part of the paper that Parham has, and in the second part of this paper they combine these two tables together and rank the batteries for different technologies. And for example, LFP it's the best one for the usually for the mobile robots, but it's basically the different.
Yeah, I think it's on one side choosing an optimal battery, which battery technology, on the other hand also having an optimized management of the battery. And for example, I have an electric vehicle, and there it's rather strict imposed to the user how to use it. So I cannot, it's strongly not advised to always charge it fully, because then the battery will degrade, and the biggest cost of my car is the battery. So the second hand value of my car is not the amount of driven kilometers, but the amount that is maintained in my battery. So taking care of the battery is becoming very important. And so also, for example, for my previous Mac, for example, due to Corona is completely the battery destroyed, because it was always fully charged. So now I have a program in it, so I can limit the charging limit, because for daily use, like now it's plugged in, and I come home and so on, so I don't need a long battery life, a lot of energy in the battery, but maybe in 2 weeks I go to the United States and I want to work the whole flight. So then I need exceptionally fully charged. And that's the same with my car. If I go on holiday, then exceptionally I do it 100%. And so I think this system has to go to robots, where we need to see what is the mission time and how much energy is required for that. And for most of the missions, probably we don't need a complete battery, because otherwise it's wrongly designed for it. So then I prefer maybe to charge it only 70-80%, because I know in my warehouse I can do with it. But maybe for some missions an exceptional charge or amount of energy is needed, and then the system can decide, okay, now I need to fully charge it. And we hope by that we can extend the lifetime of the battery, and so also have a kind of return on investment, because that system will have a certain price, but the return is that the battery can be extended. And that's, as I mentioned, we have now robots, and I went, for example, the whole time we don't have projects anymore on the now robots, that orange robot, and so I used it for my son is 3 years old, and I had to read books in the school, and I took the robot, and after 10 minutes it said, yeah, my batteries are empty. The reason is it's totally not managed. It's always empty or always full, and so the batteries degrade enormously. Why? It's the use of the battery, not the battery itself, that is the problematic. It's a combination, but I think we can as such be more sustainable.
But in that case, if we consider a battery with a higher capacity, will last longer.
Yes, that's true, but it's also a higher battery means that I need stronger motors to do it. Stronger motors needs that I need more battery in it. And so the next speaker is also Pablo, who will also discuss that we need more energy efficient drivetrains and especially the gears, because it's a negative loop. You need more battery life, so you need more weight, more materials, more weight in the robot. So to do that, you need to carry, to have stronger motors, but stronger motors need more batteries, and you go in a negative loop. So that's the reason why we want to take better care of the battery, to make it more sustainable, because for such a humanoid, if you can already run such a short time, if 80% is only remaining after a few years, that has a huge impact on that robot.
Other questions?
If not, then I think we can have a break, and I propose to come back in 15 minutes, so 15 past 3. Is that okay, Anja? Okay, thank you. Sorry? Thank you, Anja. Test. Okay, perfect. Okay, we will start again with our last speaker. So I think we have a quite diverse amount of speakers, not in gender, and we hope we have already several female researchers in our group, but we hope for much more. But also I think diversity is also persons with a very different background. So Pablo has a long career in industry, being CEO and so on, and then he decided to start a PhD. So not a classical road, but I think it's very interesting because he brings a lot of knowledge on manufacturing and OEMs and so on in our research group. And he also works on making robots much more energy efficient by working on gears, which are extremely old. Gears exist for a long time, but I think Pablo can prove that you still can innovate in gears to make more sustainable robots. So please, Pablo, the floor is yours.
Thank you, Bram. Maybe to start with, one of the things about diversity that Bram did not mention, of course, is age, but it is also an important point. I'm not in my 20s, as you can see, and that is part of this diversity aspect. So it's going to be about gearboxes, so it's going to be about mechanics. Yep. Sorry? Further, okay. Like that, you can hear me? Yeah? It's good like that? Okay. So yes, I'm Pablo. I'm currently a postdoctoral researcher at the Vrije Universiteit Brussels of the Brubotics group. I hear that Louis already introduced you a bit our group and what we do. So we work on collaborative human-centric robotics. That means devices like the ones you see here. The pointer doesn't work here. I didn't. So cobots, service robots, including humanoids and this type of service robots, prosthetic devices that can basically help people who have lost a limb, or exoskeletons that can go in industry to help people doing heavy work to unload their musculoskeletal system, but also to recover after, do rehabilitation after some injuries and things like that. This is the type of devices we work at. And this is the main problem that we face, robotic engineers, is that we see all the potential that these robotic devices have to improve the lives of so many people. So we try to build them, and we start with something, an idea like Elon Musk on the right, and we end up with a beast like Elon Musk 9 months later, and which is clearly too heavy, too rigid, too expensive, too slow, too dangerous, too a lot of things, including energy intensive. And after doing research in this topic, in this human-centric topic for over 30 years, this group got to the conclusion that actually gearboxes were at the core of this problem, were a pivotal issue that we had to solve. And interestingly, we see more and more people in the robotics community getting to that conclusion recently. Luckily, we started working on that 7 years ago when I joined here. And Professor Dirk Lefebvre had to convince me that gearboxes were a problem. Me coming from 20 years working in the automotive industry, I was convinced, hey, actuation, we know that, okay? We are really sophisticated in actuation. It exists, I will find it for you, and then we'll figure out another topic for my PhD. I ended up doing my PhD in a gearbox, of course. What is the problem? Well, the problem is that we are using gearboxes that have not been conceived for human-centric robotics. That's the point. We are using gearboxes that have been conceived for industrial robots that move very accurately, very quickly, with very high payloads. But I like to make the joke, I don't know, at your places, but at my place, things are not positioned within microns, okay? So that's an overkill. We're using a technology that is extremely good at positioning with very, very high accuracy, but our homes are messes and our offices too. So we don't need that, and this is very expensive to get that. So we started from the idea, okay, it's a bit also my background coming from automotive is you first understand the problem and then you specify what you're really looking for. And that's sometimes a bit hidden. It's not what you thought was the problem at the beginning. So what we saw is that there's 5 parameters that are pivotal for, in our opinion, for human-centric robotics. The first one is torque density. The explanation is simple. Those of you who work with people know that better than me. But if any of you went for a run this morning, your foot has been developing, each of them, pretty much the same torque like a Formula One engine. The difference, of course, is in the speed. So Formula One engines will turn at 18,000 RPMs. I don't think any of you can make it more than 120. Me, certainly not. So the power density of an electrical motor is very good. And we can do really wonders with electrical motors when we put them in machines. But when we try to use electrical motors to replicate how we humans move, torque divided by weight is a fundamental challenge. That's, for us, is the first and the most important one. On top of that is cost. If we want to put these devices in the homes of many people, we have to make them much cheaper. Right now, Tesla bot is over 1 million cost, basically. Efficiency, we've had very nice presentations from Parham today about that. Back drivability, which is something I will be talking also a bit later. And noise. Now we're not anymore in an industrial setting where there's a lot of machines making noise. We may be in a concert room, we may be in a home bringing our kids to bed, so it cannot be noisy, okay? Noise is a very important thing also. If we translate that into gears, well, actually it translates quite good. The requirements are very similar. For a gear, it means that we need a very lightweight gear with a very high gear ratio. I will explain that immediately what it means, but this is connected to the lightweight characteristic of the robot. It needs to be back drivable. Again, the second time I promise I will explain that. It has to be very efficient because we are basically deploying the batteries that our colleagues are so carefully charging so that its lifetime is very good and we just burn it. Then there is complexity, which is basically linked to cost. If you increase volumes, like what we do in automotive, what you end up with is that parts which are complicated to build are expensive. Parts which are simple to build are cheap. So the way to reduce cost is to go for simple manufacturing, and then noise and vibration of the gearbox. I'll go now slowly through each of them. Let me first start with why is weight so important? Weight is important because if you want to be close to a robot like the one I showed before from Elon Musk, you will not feel very comfortable when it starts moving quickly because it's a heavy beast, okay? So if it hits you, it's going to hurt a lot. So weight is very important, it's directly linked to safety. But there's an effect called compound mass effect, which we also see, for example, in planes, which is when you take, for example, a cobot, your actuators are moving mainly robot and a little bit of payload. This is the example you see here, is a UR5 with a payload capacity of up to 5 kilos. So most of the time it's not moving 5 kilos, it's moving less than that. And the movable parts of the robot weigh 16.6 kilos. So actually you're using your actuators to move the robot and a little bit of payload. So what happens if we can reduce the weight of the actuator, gearbox plus electrical motor, by 30%? Well, all of a sudden, your robot is lighter. And that means, hey, you need lighter actuators because now you're moving a way less weight. So there's a chain effect that actually shows that if you reduce by 30% the weight of the actuators, the outcome is now you have half the weight of the robot to move the same payload. So you're lightweight, but you're also more efficient because the only thing that counts for your efficiency is the payload that you have. So you're moving less weight for the same payload. You're also cheaper. You've just saved half of the material of the robot because the robot weighs the half. So weight is the way. For me, weight is the first, second, and third requirement for human-centric robotics. What does it mean for a gearbox? It means that we have to go to high gear ratios. Why? Because motors, the weight of a motor is proportional to the torque. Motors, generally, they like speed. They don't like torque. That's going back to the example of the ankle and the engine, for example. It's the same for an electrical motor. They are good at developing high speeds and can achieve very good power density. But if you want them to deliver high power, high torque, they become heavy. So the way to achieve a lightweight actuator is to go to a very high gear ratio. So your gearbox is bigger actually than your motor in terms of weight and size. This is some examples taken from catalogs that show this trend, this proportionality basically between a motor's torque and the weight. Efficiency. well, behind this relatively complicated equation, there's two things, important things to understand here. The first one is we're in a gearbox. We are mainly looking at the efficiency losses between the teeth, and this is very important because gearboxes are complicated. There's a lot of movement inside of a gearbox, and there's a lot of things that contribute to losses. You can think, for example, of what we call the pocketing of the grease. So the grease is basically going to be between the teeth, and you have to smash that teeth so that the force is transferred. This generates losses. There's also splashing of the oil or the grease that you basically have to move as long as you move. So there's a lot of sources of movement. Good news is we can focus on only the teeth, because the losses there are so high that all others are not relevant when we are looking at high ratio gearboxes. And that's what we did. And what we saw is that there's two main components for the losses of a gear. The first one is the efficiency in the tooth contact. So basically, what is the shape of your tooth, etc., so that you're actually transferring that movement with a minimum of sliding between the tooth. And the second thing is something that is called latent power ratio, which basically tells us how much relative movement is there between the gears. Because what is important for losses in a gearbox is not the absolute speed of a gear, it's the relative speed of one gear to another. Your losses will be proportional to that. And to illustrate that, let me try to show you here. This is one way of using these two gears. This is another way of doing that. And this is another way of doing that. If I have exactly the same teeth, the same forces and everything, the losses will be completely different because the relative movement between the two gears are completely different. So you need to take the two into account. Back drivability, probably my favorite subject, I have to say. So what is back drivability? I think the best way to illustrate that is to show it to you here. That's why I brought my demonstrator over here. I will come out of the camera, but that's fine, I think. So what you see here is a demonstrator of, inside here there's our gearbox. This is the input to the gearbox, and the big wheel here is the output. Okay. So normally, if I turn this guy, you can see I can turn it very quickly, and then the output turns very slowly. That's the gear ratio. Is the relationship between the two speeds. Okay. So what is back drivability? Is you take the output and you spin the input. That's back driving. Okay. Why is this important for human-centric devices? Because we humans use back drivability all the time. Animals in general. Let me give you one example here. Now, those of you who have a mechanical engineering background, try to think how would you make, in which materials would you make the legs, the feet of this animal to reproduce that, to overcome all the impacts, all the impacts that basically this is seeing. So how do we animals cope with that? Well, basically what we do is, there's a lot of things that play into that, but the main thing in terms of back drivability is we're not using just our feet. We're sending the energy through all our body. So the goat is using basically the full body, and that means that it has to send the impact from the feet to the rest of the body through the joints. Okay? Is that clear? This is a very important topic. It has other important elements. This is, by the way, the example of the 300 Newton meters that I mentioned if you went for a run. That's the number you have. You're beyond 300 Newton meters, which is basically a Formula 1 engine. But I mentioned that because it's a bit more complicated, but actually we also use the back drivability to achieve this very high torque in a very small angle. Okay, so back drivability also very, very important. I think he did not like the video. Oh, yeah, it's all on me. It's all no problem. We will be back. Mathematically, it's a bit more complicated than on the goat, but the principle is there. Is what we call mechanical impedance. So you basically have to look at your equations of movement. That's how we called it, mechanical engineers. But the principle is that. And what is also interesting here is that the two main elements in this equation are actually inertia and Coulomb friction in the case that occupies us, which is gearboxes. We're almost there. The next ones are a bit faster. Noise vibration harness. So when you have gears turning and meshing with each other, you generate quite a lot of noise. If you go to high gear ratios, which is how we solve the weight problem, and that is the problem, so anything else becomes lower priority, that means you're going to a high frequent range of noise, which we humans don't like. So we're not very objective in how we feel noise, but high speeds, we don't like them. The good news here is that the car industry is facing exactly the same problem. As they took away the combustion engine, that was the big noise maker in the car. Now, basically, they remain with gear noise as a main contributor in an electrical car. And so they are doing a lot to reduce that. So basically, our expectation is they will solve that for us, kind of. Yeah. You can do a lot on the manufacturing. I can already tell you a bit. The idea is you introduce some textures on the shape of your teeth, and through those textures, what you do is you perturb these basic frequencies, and in this way, you damp them in a way. So there's very creative solutions coming there. Manufacturing complexity. These are the three technologies that you can basically use for creating high gear ratios. The cycloidal drive is what is used mainly in industrial robots. For us, it's too heavy, and I told you before, if it's heavy, it's not an option for me. So this one went away. Harmonic drive is what you find in basically at least 90% of the robotic, human-centric robotic applications that you see. So if you think of humanoids, on the legs, they may be using some other solutions, like Tesla, for example, use some other solutions, but most of the joints in humanoids, the practical totality of cobots, they all use harmonic drives. Very complicated, very expensive, so I didn't like it either. And planetary gears have been around since 3,000 years. So the Chinese were using them already 1000 BC. They build a wood, they call it the south pointing chariot. I tell you, it's an interesting story I find. It's basically a wood chariot that when it turns, there's a wood guy on top of that is always pointing to the south. And when it turns, the gears make so that wherever you bring the chariot, it will always point to the south. 1000 years BC. Okay. So the good thing about planetary gears is that we know them very well. They have been with us for 3,000 years. You find them in the best masterpieces of engineering today. Helicopters, submarines, they are everywhere. So they've been with us for 3,000 years. They are extremely versatile, and we can make them cheap and effectively and quick. So we said, this is the way to go. And this is the way we went. We went for planetary gears because they can provide very high gear ratios. They have good efficiency, and they are backdrivable. In the last 7 years, we've built over 25 prototypes. Quite some prototypes, from plastic to steel to understand all how these principles work, etc., etc. We have developed a new technology, which is based on an idea that is over 100 years old. As Bram mentioned, a German engineer called Ulrich Wolfram came with this idea 100 years ago. His problem was efficiency, and for us, efficiency was not negotiable, so we figured out a way around that problem, but we basically start from his idea. It's now patented. It's a patent that has been accepted. And that means we have lightweight, we have efficiency, we have backdrivability, and we have easiness to integrate. It's a disc shape. We now have affordability also. Now we have quoted them for series, so we know they are affordable. And now we're building the prototypes so that in the second quarter of 2024, we can confirm, okay, where are we on noise? Where are we on backlash? It's not critical for us, as I mentioned before. We are not aiming at position and accuracy. That's not how we move. I explained that to my robotic, industrial robot friends and customers, saying, look, if I approach anything, I use my eyes to approach, so I have an accuracy of maybe plus minus 1.5, plus minus 2 millimeters. From the moment I have contact, I don't need my eyes anymore. It's force feedback. So what we have to be very good at is force feedback. And there you can think, if you have a very transparent gearbox like that one there, where I can basically drive from the output and the input turns, that means I don't need a torque sensor to achieve dexterity. I can use the muscles, I can use the motors in my robot to feel what the fingers are doing. And this is exactly how we do it. we don't only use skin. We don't only get feedback from our skin. We use the whole motoric to provide feedback to achieve dexterity. So this gearbox, contrary to the harmonic drive, is more efficient and is easily back drivable, which means we also open a road for another level of dexterity. So I think by this time, oh man, I think this guy needs replacement soon. Huh? He's been with me for a while, but I didn't thought it was that bad. So I think you've noticed I'm quite passionate about this. It was not my plan. I came to academia after 20 years in industry with the need for doing more, digging deeper into the problems that what you do in industry. But it was not my plan, but now we are totally launched. So we want to build a company. We want to build these guys. We want to bring into the market. We're collecting, looking for investors to do that. We have a first investor that has said yet. And well, the future is huge if we can really make it work, because it's not just human-centric robotics, which is already a lot and is growing at an incredible speed in terms of market, but it's also excavators. If you think of that, we actually move closer to an excavator than to an electrical motor. We don't spin our hands very quickly, but we can develop a lot of force. So it's actually closer to an excavator. And wherever you have applications where the speed is not very high, but the forces are high and weight is important, well, I think the same principles that we have solved here apply. This is our plan, and we are totally committed to bring that into action. I have actually a personal commitment to this, which is I don't want my daughter to feel bad for bringing me into a senior residence. I want to buy one of these Tesla robots or whatever they are so that I can live on my own in my own place for very, very long. Thanks a lot, guys.
Questions?
Yeah, thanks a lot for the presentation. Very interesting. I was just a technical question for the backdrivability. So you mean like the induction of energy, like using the motor as a generator and then measuring that force or like the whatever.
Yeah, it's the same principle. So actually, if you're doing energy recovery or regeneration, as we normally call it, you need to be backdrivable. You need to be able to put the forces from your load back to your motor through the gearbox, and that's not possible with the current solutions. The current solutions they have a very, very high. You need a very high force to move it. To give you one example, if you're wearing an exoskeleton with these harmonic drive systems that I mentioned before, the battery is deployed. You cannot move anymore. Somebody has to come and help you out of your suite. You're blocked. You cannot move anymore. So this is it's totally aligned with that. Yeah.
And maybe then follow up. Have you also thought about maybe, I don't know if the English word is the same, recuperability? So maybe use movements. I don't know. You lift something up, and when you lift the arm down or you let it down, you can recuperate energy, and so maybe save or gain energy.
Yes, this is indeed. This is an enabler of energy recovery or regeneration is the name that we normally use, at least. Again, let me go back to an excavator. I was yesterday presenting in a different context the possibilities of using that in heavy duty, and an excavator is a good example. You lift the load and then you lower it down. So, so much energy bringing it down that you can actually reduce the size of your battery by a factor. And similar things happens with us humans, because we do a lot of regeneration ourselves. We are most of the time, or a big percentage of the time, not in the energy providing, but in the energy recovering phase. So yeah, totally in line with that.
Another question?
So I imagine that your one of the biggest challenges you had to face is how to deal with friction. So can you tell us something about, let's say, the research behind it? Because I'm quite curious.
Yes, indeed, friction is efficiency is what we show there, and what we also discovered is that backdrivability, we were aware that it was very important, but it was like the third in our list in terms of what we needed. And what we found is if we make a gearbox that is very efficient, it is automatically backdrivable. So we built our prototype, and then efficiency was quite good, and then all of a sudden we could do that. That's how actually the idea for that demonstrator came. That's the first gearbox we made that was high efficient, and I could backdrive it. So we thought, okay, let's do a demonstrator with that. How you do that? If you are into gears, what happened in gears? Let me go quickly here, and I will try not to go too deep because I can enjoy that too much. But basically, what you have is compared to friction only, which would be the friction coefficient. In gears, you have a factor, a form factor that depends on the shape of your gears. Okay. And that means by means of playing with the shape of your teeth and deviating from conventional tooth geometries, you can actually optimize your teeth to improve efficiency. Now, why is this important? Is because if you see the latent power part that you see here, this relative movement between parts is a multiplicator. And that's very interesting because in a normal gearbox, you can actually achieve 98% efficiency. So you can achieve very good efficiency. So the question is, would you make the effort to make a special teeth to go from 98 to 99? Probably not. But if I tell you LPR, the LPR is 50. So that means you have the losses 2% multiplied by 50, you have 0 efficiency. And now you go to 99. So you have 1% multiplied by 50, your efficiency is 50%. What means that a little gain in a little reduction of losses in terms of absolute value, going from 98 to 99%, is a huge reduction, relative reduction in terms of losses. And you have someone here multiplying that by quite large numbers. So that means for us, it is worth to go the extra mile into optimizing these two geometry to as much as we can bring it, because every 0.05% we win is magic. Is fantastic, and that's basically the first part. The second part is we came up with a deviation from the original design of Ulrich Wolfram, the German engineer, so that we could reduce the LPR. Mm-hmm. So we rethought a bit the gearbox so that the relative movement between gears are minimized, brought to the minimum, and it's the combination of these two that allowed us to go for, let's say, a gear ratio of 250 to 1. That's what we are aiming at right now, 250 to 1. We can go beyond, but we feel this is the sweet spot. Mm-hmm. We think that a 90% efficiency is feasible. We have not built it yet, but those are the prototypes that are coming in 4 weeks. So I'm really looking forward to see the part and see if they do that. If you would use a conventional Wolfram design, your efficiency would be 25%. Mm-hmm. So you're burning 3/4 of your battery on that, which is terrible. But a harmonic drive is a bit better, but it's not much better. So a harmonic drive, if you look at the specifications, the peak efficiency is 82, 85%. It's not 50%, it's not, yeah, but that's the peak efficiency. In a robotic cycle, like we mentioned there, where you're doing this all the time, most of the time you're not there. And the harmonic drive is extremely sensitive to the operating conditions, which means that this is a typical robotic cycle. This is the real efficiency. The effective efficiency you get is under 50%. So currently you're burning half of your battery in heating up your gearboxes. That's how all these devices that I mentioned before that have harmonic drives operate. They use half of the battery to heat up the gearboxes, which means the potential is huge to improve on that, and also to reduce the weight of the battery, which again, same effect of escalation, etc., etc. So we think the leverage is huge. We still have some technical challenges, but that's the idea.
So if I will understand, one of the bottom line of the story is that, so one of the results is also that the going a little bit astray from the classical tooth geometry that has been defined at the end of the 1800s most of the times can still give more advantages. And the question is, usually when you get an advantage in one end, you get some drawback somewhere. So what is the drawback? I imagine fragility or something like that?
Is the rating. The rating is slightly reduced, so you have to find a balance between the two. Mm-hmm. But in this configuration, when you start playing with it, which I think we believe is the reason why nobody came up with this idea before us, because I mean the basic technology was lying there for 100 years, and it's not that we have not used it. In World War II, Wolfram gearboxes were used in airplanes in propellers and things like that. They had the problem of efficiency at that time. So it is because it's quite counterintuitive. You have to do something quite counterintuitive, and then you realize, oh, there's a lot of nice things that start happening when you start doing that. And that's exactly what happens with this. It's unforeseen things that start happening and playing for you that compensates. To put it simply, we increase the size of the gearbox by a little bit, which of course was against our idea because we want to be lightweight. So it's no. If you go to a high gear ratio to be compact, you don't increase the size of your gearbox. We did that. And through increasing that, we managed to reduce the size. So there's some magic happening there that actually makes, you increase it first, but then you can reduce the complete size again. So you actually gain weight by means of doing that. And that's linked to the choice of the teeth and the fact that, okay, now we have more flexibility in terms of the rating of the gearboxes. We can actually force the gearboxes a bit more, make them a bit bigger, because our gearbox is smaller than an original Wolfram. So that is a bit how this comes. It was quite counterintuitive. As an anecdote, it was our promoter's idea, and I was working with Stein Crispel. Some of you know him, and we came out saying, I mean, how do we tell Dirk that he is completely wrong? He's increasing the weight of the gearbox. But okay, we know Dirk quite well. You don't tell him, you prove him wrong. That's the only way. And so we tried to prove him wrong. And another time, like what I said with the gearboxes when I started here, he proved us wrong. And yeah, there was a lot of magic there, but it was completely counterintuitive. And we were already 3 years into planetary gearboxes. So we knew what we were doing. For us, it was madness doing that. But yeah, as I said, Dirk, you don't convince him, you prove him wrong. That's the way. And yeah, that's how we got there.
And last curiosity, how much tolerances are reduced doing so? Allowable tolerances.
You mean like backlash or?
No, I mean in fabrication, you have to be more precise to do this kind of to use this kind of approach.
This is the question that we are still not able to solve. I mean, it's not a 0-1. It's not a digital question in that sense. The question is where is the sweet spot again? Because if you go to very high accuracy, your efficiency will be better, but then of course the cost will be much higher. And this is what we are trying to figure out. But the problem with gears is if you want to make gears that are representative for these type of questions or robustness, for example, you have to spend 50,000 euros to make the cutting tools so that you can cut tools which are representative, and then you get to the level of efficiency that you can do, and then you can do this type of analysis. Before, we didn't even try because we know it's worthless.
So, thanks, Pablo. You talked about noise. How do you engineer noise? Do you just make something and then evaluate the noise, or there are some parameters? Just friction or something else?
So the noise in the gearbox is mainly generated by the change of stiffness. So when you have a gearbox turning, there's moments where you have only one tooth engaged and moments where you have two tooth engaged, and then at different angles. And that means the stiffness of the system is changing regularly. And this is actually what generates most of the noise in a gearbox. So the way to compensate for that is basically to calculate the number of teeth and play a bit with the number of teeth such that you can play with that. And then, as I said, there's a lot going on that in the manufacturing side. What they do is they add some texture, so they include defects, so that this repetitivity of the number of teeth is not completely there. They have something that breaks that, and by means of doing that, the trick is you move your frequency to somewhere where you're less sensitive to. That's, again, noise engineering, yeah. So we're still not trying the idea that the car automotive manufacturers tried some time ago to put some additional noises in there to make the noise of an engine. I don't know if you guys are aware, but there was something that was tried. So basically, because the noise of the engine was gone and you were hearing other things, they put something that created the noise of an engine. Also to warn people, because people will not hear the cars and there was a lot of accidents. So this we're not trying. We're trying to go to a bit more sophisticated solutions, yeah. But there's a lot coming there on the car industry. We are members of the American Gear Manufacturers Association, which is basically the the association in terms of gears since 100 years. They have most of the norms that are out there are either from there or derived from there. And we've been there a couple of times. Last time was with Anand when we were there. And so we talked to these people, and I'm convinced they have that under control. So for us, when we get there, they will have a solution for us. If we have a problem, which we will know now. But chances are high because we're using high-speed input motors, and that's always a problem. You have a high-speed excitation. Yeah.
Yeah, again, as a former teacher in construction design, I'm interested in your planetary gearbox. Is it like a Ravigno planetary gearbox? Do you use multiple stage gearbox, planetary faces, or is it like a simple one and you're not changing gears? It's just like one static translation of power?
It's a bit Ravigno, but it's not exactly Ravigno. Is a compound planet gearbox. That means you have two ring gears, and your planets have two stages, which means they engage simultaneously with the first and the second ring. And what happens is, if you hold one of the rings fixed, there's a quasi-equalization of the speeds of the two rings happening because the relative sizes of the ring to the planet are similar, which means, okay, one is hold, the other one is going to turn at relatively slow speed, no matter how much speed you put in your input motor, which means your ability to create huge gear ratios is total. You can go to thousands, you can go to tens of thousands. It's the cost of that is efficiency. You lose efficiency. But the beautiful thing about that is that you're not dependent on the number of teeth. The harmonic drive is. So if you want to have a higher gear ratio, you have to put more teeth there. And they have to put 2 times the number of the gear ratio. So if you have 100 to 1 gear harmonic drive, you have 200 teeth there. So very small, very difficult to manufacture. That's why I explained the complexity. In our case, we can do that with, it's not dependent. We can do that with the number of teeth we want. And that means you tell us the torque, we tell you the size and the weight. And then the gear ratio is for free except for the drop of efficiency, which is what we have optimized. This is very powerful because then you can go with a quick motor that is very lightweight. Yeah.
We have a last question from Teams. Hi, Sharada from Profactor, Austria. I have a general question, not an expert in this. What are the potential problems, barriers in bringing this technology to the market?
Oh, you want me to do another presentation? I had yesterday one with we are following the European Innovation Council. They make programs for accelerators, and they have one which is called T2M, time to market, particularly for deep tech technology, let's say. So the course lasted 8 weeks. And so we had to do yesterday a presentation of, okay, what have we learned? And let me try to picture that like that. It will probably not satisfy the question, but that's the best I can get. Is when we started, we were sitting on our gears for robots, and we thought, well, we know these gears, we know the challenges, we still have a lot to do, we'll be busy with that. And then you say, okay, I want to go to the market. And then you start seeing things passing like, okay, you have to get money for doing that. So you have to find an investor. You have to convince an investor. He wants a pitch. There's going to be a term sheet. There's going to be a shareholder agreement. Oh, you have to hire a lawyer. And then you have to figure out, okay, is the conditions that they're giving to me okay? What about the valuation? All these things started to appear all of a sudden. And you say, I just want to go to the market. It's a great idea. I mean, can I not? It's a very, very complicated thing. Challenges are everywhere. The one thing I have definitely learned is play scenarios. You have to think, what if? It reminds me a lot writing the thesis.
Okay.
So when you're doing your research, you have it in your head and everything makes sense. Then you sit down to write your thesis and you realize, oh, I made a big jump from here to there, and it's not logical at all. There's something missing totally in my reasoning here. And this is the same. It's full of that. So you have to think scenarios. You have to write them down. The tools are there. You have to take the time to master them, but the tools are there. But you have to take the time to go through them because they will force you to identify incoherences. And you want to identify them then, and not when you're pitching for an investor who says, this guy has no idea, so I walk away with my 2 million that would have basically brought us to the market. Yeah. So that's it's a lot of work, prepare for several months of focusing on learning what it takes to bring a technology to the market. The other most important thing is traction. So approach your customers, potential customers, the sooner the better. When we do development, we feel very uncomfortable with talking about things we don't know. So the last person you want to go and talk about your product, which is completely not baked yet, is your customer. But that's what it takes. You have to go there and you have to get it in your nose and say, oh, okay, yes, because that is the fastest way to the market, is to get it in your nose and get it wrong. So go to your customers, talk to them, make sure that you get customer traction, that you've spoken to them, that you understand their problems, and then you go for them. And we started from a problem that we knew here from 30 years of research was there. And we thought we knew it, and it was still by far not enough. We've learned so much about where the problem is by talking to these people. We thought it was efficiency. We're engineers, so we want to be efficient. That's the one thing where we start things. It's like, if you're not efficient, it's not a good solution. You go to ABB, for example, a robot manufacturer, and you tell them, yeah, we can improve efficiency by, you can reduce your losses by a half. So I don't need you. I'm plugged to the wall. That's almost free. Okay. What about devices that are powered on batteries? So harmonic drive is 90%, 85%. It's good enough. Said, no, it's not. You're building robots and you don't know that. And they didn't know. They didn't know. People building robots for ABB, they didn't know. Good engineers. The focus was not there, so we had to completely change. But that's the good thing. Then you really understand your product and you realize, no, it's weight. It's weight. We enable you to reduce the weight of your robot by a half. It's safer, it's faster, more productive, it's cheaper, half the material, it's more efficient because you're only interested in the payload. So everything is through the weight. And then that story is, yeah, it's taking a different way. Still by far not there, but at least we've started the path. I like to say we have a plan. We'll see how long it takes us, but now we have a plan. We had no plan when we started here. We just looked up and say we want to go there, and then a lot of things started to be in the way and say, how do we do that? Now we have a plan.
Okay. I think we have time for a very short question.
Yeah, since you're talking about the gap between the market and the science, I was wondering about the freedom to operate when going to investors. You need a leverage, the IP protection, intellectual property protection. How can you do it if you are stating that this technology has been in the public domain for 100 years? So how can you protect yourself against a company getting a copycat of your technology?
It takes a lot of work. When I started working on this, Professor Lefebvre, told me, I have read over 200 patents. We're clean, there's nothing on that. So I started doing my homework and I found Ulrich Wolfram, 100 years old, and then it started to pop up in books, not in patents, in books. So it's like, okay, it's over. I think I'm not exaggerating if I say we've read, together the three of us, over 2,000 patents in the path there. And that's what it takes. If you want to put, it depends on your landscape. In our case, gears have been around for a long time. It's a mining field. So when you try to place a patent on gears, it's a mining field. So you have to do your homework. You have to really know where you put it, and then come up with a strategy, understand the language, the low language of the people you're talking when you're writing the patent, because that's another problem. I can explain my gearbox quite well to an engineer, but how do I explain that such that it's compatible with a law and people can prove it and all that? It's another. It took a lot of time, but it pays off. We managed to plant what we call a broad umbrella patent. That's an interesting concept. So you try to cover, you try to be as generic as possible with your first patent, so that you have a broad umbrella where you can do research, because you still don't know exactly what is the best solution. And if you know that, it's probably too late. So you have to start earlier than that. You make the big umbrella, and then you say, oh, this is the one that I really like, and then you create your second patent. but the first one should be a broad umbrella one. And that's a difficult one because it's a mining fell, so wherever you step. And I have to say now is maybe every month or 6 weeks, I get almost a heart attack because there's another patent that comes and I open and say, oh no. So I wish we have the patent, but even having the patent is not enough. The patent attorney, the patent prover may have missed something. And if it's out there before yours, you're in trouble. That's the freedom to operate, basically. Yeah. That's what it takes, is that jump. A clean report of the patent office is very useful. So when we talk to investors, we had no novelty comments and no innovation step comments. It was clean from the first step. And that simplifies this discussion by a lot. But I cannot tell you how many hours it took us to do that. So the first movement we did, we were 3 years working on the patent, basically. During 3 years working on the patent. Before we filed the patent and said, okay, there it goes, let's go for the best, and the outcome was quite good. Yeah. A very, very interesting topic. Yeah.
Okay, I think we can go towards the end.
So thank again to Pablo, to the last speaker. So we end here for today, and I want to remind all of you that next week we have one of the big events of the BrIAS season. That is our first forum, so our first 2 days conference. It will be on Thursday and Friday in the center of the city, near the central station at Fari. For all of you that have not yet registered, please do so, and please also diffuse the good news of our conference. It will be on precision agriculture, so from robotics in agriculture, seen from different viewpoints. So we will have roboticists, we will have agronomists, we will have also historians and representatives from FAO to discuss about both technical, societal, historical aspects on what robotics can do for agriculture. So I hope that all of you will be there, and this is the classical, very pressing invitation, or very threatening one. Decide what you prefer, and for the rest, so see you next week.